Welcome back to the next part here, in which we're going to talk about arrays and dynamic collections. So Java supports basic arrays, as we've already seen, using C-style syntax. In other words, it uses square brackets to access an individual element. It uses the standard zero indexing. In other words, the first element is at index 0. The second element is at index 1. And so if you've got 5 elements, the last element will be at index 4. So it's always off by 1. It always starts at 0. You can create arrays using the new keyword. I'll show that to you in a second here. But once you've created an array, the size is fixed. It can't grow, it can't shrink. It's not dynamically sized. In other words, we sometimes call this statically sized, but they are not static arrays. The nomenclature can vary from language to language. But on the other hand, there's no bookkeeping. With a programming language like C, if you ever have an array and you want to pass it to a function, you would also need to pass in a variable that indicates the size of that array, how many elements are stored in that array. With Java, we have that automatically using a .length property on the array, and I'll show that to you in a second. Also, there's no garbage collection. Once you've created a new array and you're no longer going to need to use it, you don't throw it away. You let the garbage collector take care of it for you. That's one of the advantages of using Java. There's no garbage collection. In other words, you let the Java virtual machine take care of garbage collection for you. You don't need to do your own bookkeeping. You don't need to do your own memory management to a point. All right, let's go ahead and demonstrate these things. So I've got an array just to play with from last time, but I'm also going to create another array. Say if I wanted an array to hold 100 integers. Here's how I could do that. The square brackets denote that it's an array. Of course, it needs a type, so it's an integer array called numbers. And I'll use the new keyword, and I want a new array of integers, and I want 100 of them. So again, I'm using the square brackets here, but this 100 is not an index. It is now a size. I could access elements from 0 up to 99 if I wanted to. So numbers of 0 is equal to 42, and numbers of 99 is equal to -3, say. Now, what happens if you try to access elements that are outside the scope? If I tried to set the element at index -1 to 100, of course it compiles just fine. But when I try to run this, there's going to be an exception here. Array index out of bounds exception, a -1. We'll talk about error handling and exceptions in a later part to this video series, but this is obviously illegal, and it's going to result, in this case, in a fatal error. Likewise, if I tried to access the 101st element, then there's also going to be an index or out of bounds exception. So we won't do that. Another nice convenient thing that you can do is if you want to see the entire array printed, there are array utilities. If you go with arrays dot toString in this case, and I pass in numbers, what this does is it takes this array and it formats it in a nice comma delimited list with square brackets on each end, and it turns it into one string. So this right here is actually one string that gets printed. And when we do that, well, we see 42 at the beginning here, a whole bunch of zeros because that's the default value for numbers. And at the very end, we see our -3. If you wanted to, you could process these one by one. So for int I equals 0, I is less than 100, say, I plus plus. Numbers, so I is equal to I times 10. So it'll have 0, 10, 20, 30, 40, etc. Now when we print this out, 10, 20, 30, the last one is going to be at index 99. 99 times 10 is 999. So we get that last element there. Again, you didn't need to hard code this. If you wanted to, you could go ahead and use numbers.length. And that stores whatever the length was, whatever the size was when you created it. Right? Obviously, you can't change it. That would be weird and stupid. If I say that it's equal only to 5 now, it's not going to let me do that because that is a read-only value. You cannot change that value. It's actually a property. It's not really even a value. That was an integer array. Of course, you could do arrays of doubles or strings or whatever you want. For example, double values is equal to new double. Say that there are 10 values here, and then values of 0 is equal to 1.5. Values of 1 is equal to 10.5. Values, the last one again would be at index 9, and it's 20.3, right? You can do it with strings if you wanted to. This is an array that can hold up to 5 strings. And you can assign them whatever strings you want. Remember, you can also use an enhanced for loop to iterate over each one if you don't need the index variable. For each string s in the collection names, print s, 1 to a line. And there we go. Now, arrays are useful, but they're actually quite limited. Again, they can't grow or shrink. If I need to create a new array, of a larger array to hold more stuff, because now my array is full, then you can't do that. I have to create an entirely new array, copy everything over, and then now I've got more room to store more stuff. Java offers a large selection of collection data structures. I'm going to show you just a sampling of just a few of these things. For example, instead of using a regular old array, you can use a list. Right? Let's go ahead and create a list that can hold a bunch of integers. So now there's a few things going on here that we're not prepared to get into just yet. I'm creating a list. This is called a parameterization. And all it's doing is saying that this list holds this type of variable. I'm telling it that it's going to hold integers. Now it's impossible for it to add something else. For example, a string that's not an integer. This is an interface, and this is an actual implementation of that interface. Again, don't worry about those until you get onto object-oriented programming. Just know that this is the way to do it. Now, obviously, there's also a compiler error here. I'm going to go ahead and import these things. If you're going to be using external stuff, and this is not external, this is part of the standard library in Java, but it is external to this class, or this class demo here, then you can import stuff, right? And to do that, all you need to do is up above between your package declaration and your class declaration is where you usually put it. You can go ahead and import whatever you want. If it's an external library, like you downloaded another library off the internet, you can import those classes and then use those classes. Here, it's already imported arrays for me from a previous demo, but I'm no longer using it, and so it's complaining about it. I'll go ahead and get rid of that. List is in java.util, util short for utilities. So there's a list utility, there's an array list utility, and anything else that you want to bring in, you can do imports. That's how you include or bring in external libraries or Java standard libraries. And now, what's stored in numbers? Well, it's empty. If I printed my collection, my array list, I would see, well, there's nothing in there, right? Well, how big is it? Well, that doesn't make it's not like an array that has a fixed size once it's created. It'll grow and even shrink if I'm putting stuff in and taking stuff out. So to add stuff, well, you just use this add method. I'll add the element 10 to it. Then I'll add the element 20, then 30. Right? And when I print this out, I'll have 10, 20, and 30. Right? That's because that's the order that I added them. Add adds it to the end. If I want to add it at a particular index, this is still a 0 index. So 10 is at 0, 20 is at 1, 30 is at 2. So if I wanted to put something in between, say I want to add 42, but I want to add it between 10 and 20, I can add it to index 1, and I'll go ahead and add 42 in there. And now when I print it, I should get 10, 42, 20, and 30. Right? So there are several add methods here, and there's actually dozens of different methods that you can check out. I've got it pulled up here. There are lots of methods. You can You can get a particular element at a particular index. You can add an entire other collection to it. You can add an element to an index like we just did, or you can just append it to the end of the list. You can clear it out and remove all the objects that you've added so far. For example, let's go ahead and clear it out, and then print it again, and now it's empty. Right? There are several methods that allow you to change the elements in there, to move them around, to manipulate them however you want. You can remove an element instead of just removing them all. Let's go ahead and remove one particular element. We'll remove the element at index 3. Right? In other words, 0, 1, 2, 3, we're removing 30. Right? And 30 is now gone. You can access individual elements by index, and it's 0 indexed. So if you wanted to retrieve an element and then print it out, you could do that very easily as well. What happens when you try to access an element that doesn't exist? Say an element at index 100. There aren't 100 elements in there. There are only 3 at this point. So we're going to get an index out of bounds exception, just like we got with a traditional old array. And again, you can use an enhanced for loop to iterate over the elements if you don't need the indexing. For each element integer I can't use x now, but I'll use y. In the collection numbers, system.out.println, in this case, I'll go ahead and print out y. Oops. Need to get rid of this, I guess. And now I can use the number, well, I'll leave it like that. Right? So 10, 42, and 20 is what gets printed now, because that's what's in the collection at that point in the program. That's a list. A list is ordered. It does allow duplicates. So if I wanted to add 2 10s in there, I'll go ahead and add another 10 at the end or something. Now I'll get 10, 42, 20, and 10. It allows duplicates. They are ordered. There is a sense of there is a concept of the first element, the second element, the third element, etc. Again, using 0 indexing. If you don't want duplicates and you don't care about order, an alternative is to use a set. And the implementation here that I'll use is a hash set. And again, we're going to have to import these. The big difference is it can still hold stuff, but it doesn't hold stuff in any particular order. If I'm adding stuff, well, there's no indexing, so you can't add something to the first index 1. Instead, it just gets added to the collection. It's like a bag. There's no order whatsoever, right? So when I print it out, say, I'll get rid of the rest of this. When I print it out, 20, 10, 30. That's not the order that I added them, is it? And that's because it's whatever order it happened to think is best, right? Underlying this is a hash table, and so it's storing things in an efficient manner. You don't need the same order that you added them in. There's no concept of the first element, right? You can't do something like int x is equal to numbers dot get the element at the 0th index, because there is no get method like that. Because it's unordered. There is no first element for you to do. So this is one instance in which you have to use an enhanced for loop to iterate over the elements in the collection. And in this particular case, it was the same order as this. That might just be coincidence. But there's no guarantee. If you iterate over a set once and then another time, likely you'll get the same ordering, but there's no guarantee on it. At this point, I also want to point out that, again, this is a parameterization. It only allows you to add integer elements. If I tried to add something that was not an integer, say a string, it's going to complain about that, because the method add integer is not applicable for the types of string. You said that this was a set or a list or whatever collection you're using at the time, and you parameterized it to hold integers. If you try to add something that's not an integer, it's going to complain about that and not compile. So you can't do something like that. Type safety is a very nice thing. It allows you to create guarantees on your collection that if I iterate over this collection, I know that I'm only ever going to be able to pull out an integer there. I do want to show you one more dynamic data structure here called a map. And in its parameterization, it actually takes two arguments. I'm going to be, in this particular example, I'm going to be mapping integers to strings. And as an aside here, in more recent versions of Java, you don't need to repeat the same parameterization here. You can go ahead and leave an empty parameterization, and it'll be just as happy about it. It'll infer it from this first parameterization. Let me go ahead and import these two. So a map is a different data structure, and a hash map is its implementation. A map maps a key to a value. So it maps a key, which is an integer, to a value, which is, in this case, it's a string. Of course, those can be anything that you want. If you want this to be map a string to an integer, or an integer to an integer, or a double to an integer, whatever you want, you can map an arbitrary object to any other arbitrary object. And note here, I am using the capital I and full keyword integer. That's because you cannot have primitive types in your parameterizations. This is not going to work. It needs these are called wrapper classes. Big I integer is basically a class version of an integer. For all intents and purposes, you can use it the same way. And there are subtle differences, but you don't have to worry about them right now. So with my map, which is I've just called M, I can instead of adding elements to it, I'm going to be putting a reference that this key maps to this value. So in this case, I'll go ahead and map 10 to my name, just as a toy example. I can map 20 to Alan. And I can map 30 to Anita. And when I print these out, I get these associations. 20 maps to Alan, 10 maps to Chris, 30 maps to Anita. Again, it's unordered. So I'm not getting the order that I put these things in because some things may not be orderable. If you've got objects that aren't, now integers and strings are orderable, there's natural ordering on them, but you could have objects that are not orderable. This is an object, here's a student, here's a student. How do you order them? Unless you come up with specific and implement specific rules on how to order those two things, Java is not going to know how to order them. So a map is an unordered data structure. If you want to, you can get things out. For example, if I've got a key, I want to know what that maps to. I can go ahead and go with m.get. Get the element that maps to 30. And that's going to be a string because I want the value and I'm giving it the key. And this will output Anita. If I ask for something that doesn't exist, the key 40 here doesn't exist. It's not a fatal error like an index out of bounds exception. Instead that key doesn't exist, so therefore the value it returns is null. You can go ahead and replace keys. We'll go ahead and make 30 now map to Grace instead. We'll put the same thing down here. And now it'll output Grace. I've replaced that key value pair. Okay? Again, you can have maps to map arbitrary objects to other arbitrary objects. So if I've got another map here, I can map a string, my full first legal name here, to my nickname. Right? And it's mapping a string to a string. Again, if you want to iterate over the values, the easiest way to do this is to iterate over for each key, give me the key and then the value. So for an enhanced for loop, each key string s in the collection my other map dot, how do I get the key values? Key set. that returns a set, much like exactly the collection that we just looked at. It gives me a collection of all the keys stored as a set. And then what I'll call it str instead. And then what I can do inside the loop is I can use that key to map to a value. Let me go ahead and put in a couple of other values here. And I get these results. These dynamic data structures are extremely useful. In fact, that's one of the themes of this course, that smart data structures and dumb code are a lot better than the other way around. That's a quote by Eric S. Raymond. We'll talk more about that later on. But using smart data structures can really simplify your programs because a lot of the problems are already solved for you if you use the right data structure.